MLPRegressor for a regressor problem. In the same manner, you can also import MLP classifier. Similarly, if you are going to solve for classification problem. So architectural, your neural network remains same, but only difference in the output side. For the classification problem, in the output side, model does not use any activation function. That is one key difference. Let us assume this is the output layer. This is the output node. For regressor problem, we take the net value itself as the output. Because we are predicting the housing value, right? Property price. So the continuous output will be training it. For example, the first record, the target is 35.5. Okay, your model produces something like 37.6, slightly over predicts. It is a continuous value, right? We will be training to produce the output in a continuous value. Whereas if you train a classifier model in the output side, you have a net, right? This f of net will be applying this activation function. This is called sigmoidal activation function in the output side, which converts your output to the class probability. So the nature of the sigmoidal function is it will maintain the total probability 1 up to 2 nodes. For example, for binary class model, if this node produces output 0.15, okay, and this node produces output obviously 0.85. So the total probability is always 1. So when you increase the node more than 2 for the multi-class problem, if you use sigmoidal activation function, what is the problem? Still you can use it, but the problem is your output probability scores are not normalized. For example, the score is like a 0.15, this is like a 0.25, this is like a 0.80. Your total, it will not maintain the total probability. So for that issue, for multi-class problem in the output side activation function, what is needed is we have to use softmax. Softmax is a kind of sigmoid activation function, but additionally do exponential normalization. What do you mean by exponential normalization? First, internally it will apply sigmoid, but whatever the value it obtains, say for example, this is the value it obtained, right? It will raise this value to the power of e 0.15 divided by summation of these three entities. E to the power 0.15 plus e to the power 0.25 plus e to the power 0.80. This is called exponential normalization. Similarly, this value, it will convert e to the power 0.25 divided by summation of, so denominator remains same, right? Total. The third value, e to the power 0.80 divided by the total. That is what your softmax will do. After this conversion, if you look at the value, if you take the total, it will sum to 1. But on the other hand, other hidden layers, you can free to use any activation. Say, for example, this is hidden layer 1, this is hidden layer 2, and this is output layer. Okay, if it is a binary, remember sigmoid activation function. If it is multi-class, more than 2 nodes, we have to use softmax. So sigmoid for binary, softmax for multi-class, and no activation function for regressor problem. Please understand the output side. Sigmoid for binary class, softmax for multi-class, and you should not use activation function for the regressor problem. Whereas the hidden layers, you can free to use sigmoid. Okay, can you see some of the activation functions are listed here? You can use a tan H. So ReLU is quite popular for images and all. Even we can apply here. What is the nature of ReLU? I told you already about tan H activation function. Tan H formula, it is ranges from -1 to +1, e to the power minus net, sorry, 1 minus divided by 1 plus e to the power minus net. This is the formula. Whereas the sigmoid is 0 to 1, 1 divided by 1 plus e to the power minus net. It's a That is the difference. ReLU, if you get the net value 15, okay, ReLU activation function applied on the net is actual 15. If it is a positive value, your ReLU will produce the positive output. Suppose if your net is minus 15, ReLU of minus 15, which is equal to 0. So graphically, you can draw ReLU something like this, like a linear function. If your net value is 5, your out also 5. If your net value is 10, output also 10. For all the negative values, it is 0. So f of net is defined as 0 if net is less than or equal to 0. Equal to net if net is greater than 0. So that is a definition of the ReLU activation function. Here logistic is same as a sigmoid, right? Both are same. But MLP regressor model understand sigmoid in the form of a logistic. In case if you wanted to explore other activation function other than the default, okay, let us go back to the notebook. Activation. Logistic. So this time you can try to validate with the different activation function. With what activation function your model gives a better convergence. Look at this. For the same architecture, okay, with logistic activation function, the bias error is very high. You have to see the syntax in what way, all lowercase. ReLU. ReLU is the default, I guess, for this. If we go with the default ReLU, or ELU, see, can you see? For the default ReLU activation function, we were getting our bias error just like the score we got just before lunch break during session 3. But when you go with the different activation function like logistic, that is a sigmoidal function, or you can try with other activation function like a tan H, like the way which is being used in the Stanford JavaScript simulation page. We'll try tan H. So still high. Okay. So the default ReLU itself is the best option here. Again, here we have a solver, right? I'll be talking about different solvers tomorrow once I introduced a Lab 4 notebook to you. Okay, until then, you please hold on about. Whereas instead of solver function in TensorFlow Keras framework, we used to call that as optimizer. So I want to introduce TensorFlow framework, then I will introduce that. And again, if you wanted to avoid overfit, suppose during the training process, if you see your model overfits because your variance error is very high, you can introduce this alpha term. Alpha term, you can give the value between 0 to 1 scaling factor. You can control the alpha term. So we can also manually initialize the learning rate if you wanted to initialize learning rate I and IT, like in our previous coding. Okay, if suppose if you wanted to start with 0.01 or 0.1, whatever the specified value, you can specify. So mostly, okay, rest other arguments you don't need to change. Okay, what are the commonly used variable for the experimentation? One is activation function number 1. Then you can change the solver, which is optimizer. So we don't want to go extensively because practical day-to-day process, we don't use Scikit-Learn library. Okay, so moving ahead, we will be using TensorFlow Keras framework only. There I will show you what are all the hyperparameter we will be supposed to tune and stuff like that. So for this, we have noticed that we have got better result with the default ReLU when compared to tan H or even sigmoidal activation function. That means the default activation function, this module uses ReLU activation. Okay, now the next step I'm going to introduce TensorFlow Keras framework for the same problem we are going to solve using TensorFlow Keras. So unlike your Scikit-Learn library, okay, here we have. Okay, before that, quickly I would like to show you how to calculate the model parameters. See, sometimes in day-to-day implementation and design aspects, manually we don't calculate or estimate all these things, but you should be able to understand what it means. Suppose when people nowadays it's very common to say, right, ChatGPT is being model, which the model is 7 billion model parameters, 10 billion model parameters. What it means that you should have an idea. For example, I would like to show you how to calculate the number of model parameters this neural network architecture has used. So how to compute 165, 60, right? Hidden layer 1, we have 100 neuron. Hidden layer 2, 55. So 13 inputs. Okay, your input, how many features? 13. X1 to X13. So how to compute the model parameters? So how many weight matrix are involved here? A weight matrix which connects input to the hidden layer 1. Okay. Weight matrix which connects hidden layer 1 to hidden layer 2. Let me call this is V. Hidden layer 2 to hidden layer 3. Let me call this is U. Okay. And finally, hidden layer 3 to output. Here it's a regressor problem. We have only one neuron. Okay, for classifier problem, for binary means 2 neurons, for multi-class means respective number of neurons. So only one neuron without activation function in the output. It's just a regressor problem. So how do we compute the calculation? The calculation goes like this. So how many weights are involved in this? Connecting all the inputs to 100 neurons here. So 13 into 100, okay. Here you'll have 13 into 100 plus 100. Why plus 100? Because every neuron you have one bias weight. Similarly, the V weight matrix, we are going to have 100 into 60 plus 60. 100 nodes connecting 60 nodes here. So 100 into 60, 60 neurons we have each bias. And U weight matrix, we have 60 into 55 plus 55. Finally, in the output side, okay, maybe we'll call this as Q weight matrix. This is 55 into 1 plus 1 bias. So this is 1300 plus 100, so 1400. Hundred into 60, 6060. Okay, this is 6060. $3,300 plus 55, 3,355 plus 56. So 9,000, nearly 10,500 model parameters involved in this. 10K model parameters approximately. Even a small architecture to solve a tabular data set, which involves around a 10K model weights. It rings. Think about it when we start using it for advanced application like images, text, speech, video, and so on. The model will involve several million model parameters according to the complexities. So how to import the next framework? For simple applications, okay, we are in the foundation module, right? We are in the foundation module. We are going to solve very simple problems like tabular data sets. And moving forward, when you start using it for advanced applications, there are two styles of programming. Using TensorFlow Keras framework. TensorFlow, why is always called, this is being called as, like a bigram. TensorFlow is a low-level backend, low-level programming backend for this. Keras is a high-level API acting as a front end. So all the layers we are going to define using Keras application programming interface. So the backend is being developed using a low-level TensorFlow framework. So basically there are two approaches. One is called sequential approach, sequential design. This is called design approach. Design approach to the software, to the context of the programming perspective. I'm talking about to the context of programming. This is nothing to do with any neural network architecture. Okay. Don't involve any neural network architecture here. This is nothing to do with the neural network. And also this is nothing to do with the data also. Don't connect the term sequential, means it's not talking about the sequential data. This is purely based on the programming aspect, based on the programming approach. Programming approach or the design approach I'm talking. One is a sequential design approach. Another one is a functional design approach. Functional design approach. Sequential means you are going to add like a chain link. Each and every block you are going to add like a chain link, just like your diagram, right? We have a diagrams. What is the diagram? You have a hidden layer 1, hidden layer 2, hidden layer 3, finally output layer. At the beginning of the very first session, I was mentioning about this classical architecture with a different name. People call this as a fully connected layer. Fully connected layer. Or you can call this as a dense layer, isn't it? Dense layer. Or classical neural network model, or even multi-layer perceptron layer. Multi-layer perceptron layer. Each and every layer you can connect like a chain of blocks, like a building block. You can keep on adding it. As you move on for some sophisticated applications, we may go for the functional design. Okay, functional design. Okay, first you get an experience with the sequential design. Okay, first of all, you have not gone through any kind of design with the TensorFlow Keras itself, because before you get an experience, I don't want to bombard with two aspects of designing. It will lead you for confusion. Okay, first we'll go with the standard design. The standard design is a sequential design. Once you get an experience with the standard sequential design, okay, tomorrow slowly I will give an exposure to a functional design. But moreover, for functional design is mostly it is we'll be using for some advanced applications. But however, I'll tell you the idea, because to demonstrate functional design, I have to use some advanced applications like object detection, or even language-based applications and all. But the idea alone, I'll tell you. So how basically the functional, why we go for the functional design. Okay, first aspect, we are going to solve it. Having said that, okay, at the end of the day, it's a programmer's convenience or the designer's convenience. See, even the same this coding itself, we can reframe in the form of a functional design also. Okay, it's a user choice. But for the simple task like this, we may not go for the functional design. That is why we go for a sequential design. So these are the two basic library. From keras.model, since we are going with the sequential design, I imported sequential. In case if you are going to do the functional design block, okay, instead of sequential, I don't use this. Instead of that, I have to install, that is import API call model, M-O-D-E-L, model. There, for every layer, I have to name the every layer. That means I have to assign a variable name for each and every layer. But here you can notice we are not explicitly name every layer. Initially, I define a model as a sequential. Okay, model equivalent to sequential. This model, don't get confused between this model and this model. This is an API. Okay, this is a library. This is a library. This is a user-defined variable. So this one I can name anything. Say for example, this is ANN, house price prediction. I can abbreviate like this: ANN HPP, ANN model for house price prediction. It is equivalent to sequential. Here, this ANN HPP, what is the first layer I'm going to add? First layer, I'm going to add a hidden layer 1. Every hidden layer is being named as dense. So as you move forward and learn some advanced applications, say you wanted to solve image-based problems, you may require CNN layer. There, CNN is part of the layer. So from keras.layers, you have to import CNN 2D. CNN 2D. How CNN 2D has to be called? It will be called like a convolution 2D. Similarly, when you deal with the time series data set, you have to call convolution 1D. So we have a layer called max pool layer. So this is end-to-end deep learning architecture. We require convolution layer or max pool layer to solve image-based problems. for computer vision applications. So here we are dealing with only tabular data set. I require only the fully connected layer. So your fully connected layer starts with the dense layer. I require only dense layer. So here M starts with a capital M. This is the library name. This is just an object, user defined object. Okay. So here we go with similarly the same manner. We go with different neurons. We start with the one layer and gradually I develop multiple layers. And also you can experiment. See, the number of neurons and activation function is very common to all layers, which is very crucial and important here is what? This is very important. Most of the beginners, they most commonly, they do mistake in this part. Are not on this basic level exercise as they move with the different type of data when they deal with, because the different type of data when they do the data preparation and finally after pre-processing, you have to define each and every data in a different dimensions. So you have to properly communicate to the model, fully connected layer. You have to say that what is the dimension of your input. So for a tabular data set, okay, we are dealing with the tabular data set. What is the variable I'm using here is input underscore dim. Since 13 features, you can directly pass. I also write an alternate for this, but this alternate is very common, very popular for unstructured data like images and all. What we use, instead of input dimension, we'll use input underscore shape. Input underscore shape. There, assume that I'm going to give the input image in the form of 250 cross 250 dimension. 250 rows, 250 columns. This is the matrix. Suppose I represent a picture. Okay. So this is a picture. Okay. Something like this. Okay. This picture, so image is like a matrix of pixels, right? The dimension of this image is 250 by 250. So here I have to specify 250, 250 input shape. Suppose if you represent a color image has 3 channels like RGB channel, red, green, and blue channel. There I have to specify comma 3. Input underscore shape. Having said that, you can also use input shape to represent a tabular data. Look at this. I have not used any braces, isn't it? Like a tuple format. Whereas whenever you use input shape, you should enclose a parenthesis. Inside the parenthesis, you have to tell the dimension. Suppose how can I use input shape for tabular data set? Here also you can use it, but only difference here is 13 comma. You should use the notation like this. Same 13, but you should enclose a parenthesis and then you should use input shape. You have to define like this. So input underscore shape is equivalent to, use a parenthesis 13 comma, which indicates it's a one-dimensional. You are going to represent the input feature 13 feature. It's not a 2D like an image. It's not like a 3-dimensional like a color image. It's a one-dimensional. So either there are two options, either input underscore dim equivalent to 13 or use this. So for tabular dataset, I always recommend this. When you move to image and other type of unstructured data, you can use this representation. So for the very first hidden layer, you have to tell, because the hidden layer one is, it's going to interact with the input feature, isn't it? Who is going to interact with the input feature? Hidden layer one. The subsequent layers are not directly interacting with the input feature because it's hidden layer 2 is going to interact with the transformed hidden layer output. Similarly, hidden layer 3 is going to interact with hidden layer 2 output. So hidden layer 1 is what who directly interact with the input features. The very first dense layer, you have to tell to the model, okay, there are 13 inputs are coming my way, that you have to tell explicitly. Rest other layer, you don't need to bother about it because the very first dense layer I have to tell. This is the last layer. You can easily identify which is the last layer. This is the output layer. Output layer. Why it is the output layer? Because there is no activation function. I told you for regressor problem, there is no activation. Suppose if you are going to design for a classifier problem, assume that tabular data set, okay, instead of house price, okay, you wanted to classify this like a premium house and this is the budget. Instead of the actual prices, you have to label it like a premium or a budget. If this combination of the features, you have to say it's a premium or it's a budget. And you are using two nodes in the output after one hot encoding. So how to design the output layer here? Dense 2, you have to specify 2. Okay, once I introduce the classification task after some time, I will show you how to perform one hot encoding using Keras utility. We have to use a Keras utility package like np.categorical. We have to use it. So using that, we have to do one hot encoding to the output. Since we have, in this case, 2, comma, activation equivalent to sigmoid. For multi-class, imagine if you have 3 class, I should use softmax. At the beginning of the session, I told you why we use softmax, because to maintain the total probability score to 1, sigmoid will not maintain 1 if the node increases more than 2. Softmax can maintain total probability 1. So this is it's going to act as an output layer, which was the last dense layer before the compilation. Model can automatically understand that as the output layer. Okay, but every layer we are calling as a dense. There is no specific name for it. Okay, whereas on the functional design, what is the only difference here is we don't start with model equal to sequential. Okay, this line won't be there. Rather, you'll be designing like this is hidden layer 1. You can call it equal to hidden layer 2 equal to. There's not model dot add. So you have to define like this hidden layer 1 equal to a dense of this. Then hidden layer 2 equivalent to dense of this. But remember, you have to provide the continuity. You have to, in the bracket, you have to say HL1. Because the continuity comes from this hidden layer 1. It is continuing to the hidden layer 2. Then hidden layer 3 dense of this HL2. So the benefit is, suppose if you can play around with the layers. Okay, some advanced tasks and all. You have to combine one layer with another layer. You have to concatenate with certain things. You have to concatenate. If you wanted to do such manipulations, okay, I can retrieve this particular layer. If at all, if I wanted to concatenate this with some other thing, I can do such activities and I can name this as a new layer or modified layer, something like this. So individually, I can extract a particular information, that particular layer object with the object name, and I can modify certain things moving forward for certain applications. So that kind of flexibility, my functional design will be helpful for me. So that is the idea of the functional design. Okay, but here we have done the sequential design. First, we'll see I started with some default numbers, how the model performed for this. If you look at the model summary, see the term none, it refers while they define the layer. See the input dimension, At nowhere we specify how many records you are going to present. This is just a skeleton. Your architecture will dynamically engage any number of training records. Any number of training records. So even when you're defining the input shape of an image, suppose imagine you're going to supply 100 images or 1000 images. I have 1000 images, I'm going to train. When you define the input shape, input underscore shape, you will just tell only the dimension, 250 to 53 channels. You don't need to tell, okay, 1000, 250, 250, 3. You don't need to tell explicitly the number of record you're going to pass here. So always your architecture will treat this as a none. That means it is very flexible to accommodate any number of training records, whatever you're going to present. So that is the meaning of none. No need to worry about this none. So the architecture, each and every layer, you can see what is this number. How do we arrive this number? Just now I told you how to calculate the model parameter. So 13 into 20, 260, right? Plus 20. We get 280, isn't it? 260 plus 20, 280. How do we got this 420? 20 into 20, because look at this. Hidden layer 1, hidden layer 2. 20 into 20, 400 plus 20 bias. Next, 20 into 40, 800 plus 40 bias, 840. The last layer, 40 into 1, 40 plus 1, 41. If you have any query on how to compute this, feel free to ask me. I can explain it. Sometimes it's very popular questions in the interview. They may say like, hey, this is something like 15332 architecture. They specify this is 15332 architecture, means you should understand 15 input. Okay, 15 input feature. There are 2 hidden layer. Okay, 2 hidden layer, and output layer is 2 neuron, maybe for binary class classification problem. They give an architecture like this and they'll ask, okay, including bias, how many model parameters this neural network uses. Many interviews, very popular question in the written round. So you should know how to calculate this. For this, 15 into 3 plus 3, okay, then 3 into 3 plus 3, 3 into 2 plus 2. So this total is the total number of model parameters. If they don't say including bias, excluding bias means just you don't add this component. Plus 3, don't add this one. That is excluding bias. So hope you understood how this number is calculated over here. So put together all, you see this architecture uses 1581 model parameters. So I told you how model automatically understand which is the last layer. Here, of course, there is no activation function. Model easily understand this is a regressor model because the last layer does not use any activation function. But assume that if I use it for a classifier problem, there also I use activation equal to binary class sigmoid. But how model will understand that is the last layer is because which was the last dense layer you have included just before the compilation process. It is a 2-step process. Like other ML models in Scikit-Learn, what you do, if it is like a Scikit-Learn library, model.fit, model.train. That's all, right? Because it is a very unified framework. You have to compile. Compile means it just prepare a backend that is like a blueprint. It will keep the entire backend ready for the computational workflow. Something like a hardwired is kept ready. The complete blueprint will be ready. In that blueprint, it is going to map your records and the whole training process will happen. So that blueprint engine, you have to prepare the blueprint engine, that backend engine, working engine. So when you prepare the blueprint engine for the computational workflow, you have to tell what is the loss function, what is the optimizer you're going to use. Okay, what is the optimizer? And these two are, see, this is very standard. Loss is very standard. You have only 3 options. You have 3 choices. For regressor problem, Okay, if you are solving a regressor problem, mean square error, MSE, right? You can also shortly refer this as a MSE, all lowercase. It will accept. Either you refer like this or like this, mean underscore squared underscore error. Both are acceptable by this Keras API. Number two, for binary class problem, we have to say binary underscore entropy. For multi-class, it is categorical loss entropy. So it's a binary loss entropy, categorical loss entropy. Optimizer, we have three choices. SGD. Apart from SGD, we have Adam, RMS prop, and Adagrad. Whereas your sklearn library uses this in the form of a solver, right? Solver. So the default solver is SGD. We can try other optimizers. So we'll reserve this discussion for tomorrow's session, final session. So today you should be able to construct the architecture using, that is the objective. You should be able to construct a TensorFlow Keras architecture for regressor problem as well as classifier problem. And how to fine tune the hyperparameter and optimize the model parameters, overall model performance. And what is the each and every the hyperparameter value signifies. Okay, to that detail we'll be exploring in the final session. To start with, I start with SGD. Please understand, I have already referred, do you remember? Whether you perform full batch training or mini batch or stochastic gradient descent record by record, this is a common term you have to refer to, SGD. Just by specifying the batch size during the fitting, this is where the training starts, model.fit. The moment you specify batch size 20, automatically it is understood. Every batch, there are 20 records. Every batch, there are 20 records. That means it's a mini batch training. How many iterations we train? 200 iterations. Verbose 1 means during the iterations, it will print the process. If you don't want to print anything, you just put verbose 0. Your cursor will be blinking. Okay, in the screen, you don't have anything in the display. Look at this. I have not passed. I have here. I have not divided the record like X train, Y train, X test, Y test. Okay, since we are going to see the k-fold cross-validation for this model, that is purposefully I have not divided it like a simple train test split. But in case if you have divided the data like this, next exercise I'll demonstrate with train and test data. So here you should pass model.fit X train comma Y train. Additionally, you have to pass this fellow also. Let me write down here. Model.fit X train comma Y train comma validation underscore data equal to X test comma Y test. Then you can pass other argument like batch size 20, epoch 200, verbose. Rest all the things you can pass. So what will happen during every iterations, you can see what is the training loss, training data loss, what is the validation data loss. Also, what is the training data. Okay, here we are moving forward when we start working with the classification problem. Assume you wanted to print accuracy at every step you wanted to see. You can also see the accuracy score also. what is the training accuracy and validation data accuracy. Since we have not passed the validation data, whatever the loss here it is printing is the training record loss, the entire record loss. So now we'll run this compilation, okay, followed by training 200 epochs. Before that, we'll check the data size is 506, right? What is the number you see here? So 26, because the batch size you specify 20 record per batch. Okay, strictly speaking, we should have 512 records, but we don't have 512 record, 506 records. So 20 up to 25th batch, you have 20 records. The last batch will have only 6 records. So how it is being performed, like epoch number will be like, say you have 26 batches, like 2, 3, it goes on 26 batches. So epoch 1, iteration 1, we present first batch. Okay, first batch. You take the total error gradient for 1 to 20 records. This 20 records. 20 record, what is the total gradient? So the individual gradient, we need to calculate delta naught for individual records. You take the total. Using that delta naught, you compute delta H. Using delta naught, you update this weight. Using delta H, you update this weight. Okay, once you update the weight, next batch you provide. Again, you do the total delta for this batch. Total delta for this batch. So batch by batch, you update the weights. Once you presented the last batch and you updated the weight, that is equivalent to 1 epoch. And you have to represent in the same way, you have to represent batch by batch for the second epoch. Likewise, we have done 200 times, we have presented the batches. First batch to 26th batch, one time. Again, first batch to 26th batch, another time. Each batch, we have 20 records. So you should understand this process with clarity. What is the epoch number? What is batch sizes? What is batch? There are 3 terms are involved here. Don't get confused between batch and batch sizes. Here, batch size is 20, number of batches 26. That means per batch, 20 records per batch. How many batches are there? 26 batches are. How many iterations? 200 iterations. So either we call iterations or epoch. So what we have done, so without train test bit, simply we ran the model. Now you can present any of training record, one of the randomly you can pick any of the training record and you can say model.predict. You can see how model predicts the house value for it. Okay. So, but that is specific for maybe you are utilizing the model like a production environment. But before that, we need to validate the performance, isn't it? Using a proper cross-val score. But unfortunately, your TensorFlow Keras framework does not have a dedicated cross-val score package. Whereas See, this is being a simpler, smaller data. It's okay to perform cross-wire score. The reason is why Keras API, they don't have cross-wire score functionality, because for the large volume of data, it is a time-consuming process. People easily they judge the model performance with a simple train test split validation itself. Because while they run the model performance, just by judging the difference between the training loss and the validation loss, they can judge whether the model is rightly tuned or overfitted. So the subsequent exercise, I will show you lab notebook 4 and lab notebook 5. We'll talk about all those things. How with a simple train test split validation itself, we can judge. Moving forward and working with thousands of images, uh, 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 even though we are not going to talk anything about convolution layer and stuff like that, being a foundation module. But however, I will next exercise, I wanted to show you how images can be used in a fully connected layer. At the first session, I told you, do you remember? One way is you have to do the manual feature engineering if you have a domain knowledge on image processing. Another one is a very simple trick you can use. Simply convert your 2D matrix into 1D raw pixels. Assume it is a 5 cross 5 matrix. You just linearize it, like flatten it, like 25 pixels, and you present these 25 pixels as the input to the fully connected layer. Pixel 1, pixel 2, 25 pixels to the model. Still technically it's correct, okay, but however your model is learning along with the redundancy. So we may not call this the perfect way to train images, but just to show you the workflow, how your model can handle images even without CNN layer or manual feature engineering. Okay, to give an exposure, there the training record is around 50,000 training records, images, and validation records are around 10,000 validation records. So, and that was an images. So performing cross-wire score for that a huge volume of record while training the deep learning architecture is practically not feasible. For that reason, they have not introduced cross-wire score as part of Keras API. But however, whenever you construct such model for a tabular data set, typically it's a small size data set, you can utilize cross-wire score by seeking the Scikit-Learn API. So since we are going to seek the help of Scikit-Learn API, I need to use a bridge package. That bridge package is called as a Scikit-Learn. The name itself suggests that the first half of the term indicates Scikit-Learn. The second half, it says that Keras. So to utilize cross-wire score package of Scikit-Learn for the Keras model, okay, I need to install a package called Scikit-Learn. So earlier I have commented this, right? Now I'm uncomment this. We are uncommenting this. Before that, you have to install it. By default, it won't be available. First, you have to do the installation. Pip install Scikit-Learn. Once after installation, okay, now you are able to run this import Scikit-Learn. What we are going to do, we are going to wrap, okay, we are going to wrap our Keras module using a Scikit-Learn wrapper function. and show you what exactly we are doing it. So whatever the code we have written, right, we are going to put this code inside a user-defined function. You know, in Python, how you can put this code in a user-defined function like this. Okay, using a def keyword, you name any model name for it, like model 1, model 2. You are assume that you try different architecture. Okay, say for example, like 50, 50, 30 is one architecture, then 50, 50, 40 is another architecture. Like 3 to 4 different configuration you have, and you wanted to do crosswell score with the help of Scikit-Learn's wrapper function, and you can perform multiple models and you can see which architecture is doing a good job, giving the best result. So I just keep two variations. Okay. In terms of number of neurons and number of layers, I have not shown any variation. See, both are 50, 50, 40. This also 50, 50, 40. But in terms of activation functions, I have a slight variation. The first model uses sigmoid, 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 and relief, relief, sigmoid. This combination. Just as a part of an experimentation, I wanted to try two different architecture. Look at this same architecture, but inside a user-defined function. Nothing changed. Okay. So this is nothing to do with the model-based design at all, what I mentioned. Okay. Same sequential design, just I put inside a user-defined function. And we name this as model 2. Okay. And this another model, we name it as a model 3. Maybe we can call the first design as a model 1. Okay, the first combination 20, 20, 40, because 20, 20, 40 will not give a good scope. So I don't want to explicitly do it, because as already we verified with Scikit-Learn library itself, 20 neuron was giving a very bad result. So we'll try these two architectures, 50, 50, 40, 50, 50, 40 with the different combination of the activation function. So towards the first step, I put this in a user-defined function. Because what happened earlier, without installing Scikit-Learn, we try to import Scikit-Learn, right? So, and then you try to install it. So you have to restart the kernel and you have to do it from there. So I reloaded this and I freshly installed the Scikit-Learn. Okay, now it's successfully imported. So this is the wrapper function we are going to use, KSAI-8. In case if you are solving a classification problem like KSAI-8, we have to use KSAI classifier wrapper. You can make a comment if you want for classification problem. Use KSAI classifier wrapper. Why we require this wrapper function? We require this wrapper function to perform cross-wire score functionality. We are borrowing from Scikit-Learn library. So just like that, you cannot pass, right? So I have a proper schema to pass. For that, I require a pipeline. Through pipeline only, you have to pass. So let us see how we are going to construct those pipelines. So it's enough for us to initialize model 2 and model 3, right? First, let me initialize model 2, model 3. So two different architectures are designed. You know it very well. Your cross-val score functionality will do the training part followed by the validation. Okay, but here explicit training we were doing it. And I just wanted to show you the cross-val score results. I have put this inside a user-defined function. And this is the place we are going to do the whole stuff. Can you see we are invoking the cross-val score function, which is part of Scikit-Learn package. But if it is a direct Scikit-Learn model object, okay, you can directly specify here. But it is not direct Scikit-Learn model object. It is a Keras model object. So you have to use a Keras regressor wrapper. Using a Keras regressor wrapper, you have to define what function you are going to use. So here I'm saying what is my build function name is DL model 2. First architecture I wanted to try DL model 2. So other parameters you should pass. For your training parameters, you have to pass the same epoch number, batch size. I'm passing the same information. Okay, whatever you specify, it is a user defined name for that particular process, whatever you are performing. It's an optional. So first in the pipeline, what I'm going to do, first the data is getting standardized. Okay, the data is being scaled because can you see unstandardized data I'm passing, raw data I'm passing. So X, Y, your data will get standardized here because it goes to standardized pipeline first. So to streamline the process, I initialize an empty list in the name of estimator. In the estimator.append, the first step is standardization, followed by it is going to invoke the model. Which model? Our deep learning regressor model of architecture 2 type, this one. And then it's this pipeline is packing the stages, right? Standardization followed by model. The entire thing, it's get packing. It's get packed in the name of pipeline. It's getting packed. So pipeline, this is the keyword, this is an API, where is the user defined name. Now inside the crosswell score, you can pass this. Now crosswell score will understand this, because using a Keras wrapper only using a Scikit-Keras wrapper, you have invoked this model. So rest other parameter as usual you pass for crosswell score, number of folds scoring, and you get the results. Okay, this is it's part of the fundamental question as part of ML library. Most of you are aware of it, but however, I just quickly tell you. You know that why neg root mean square error? Actually, it's RMSE score, because all crosswell score by default, even if you don't pass the scoring, you know the default scoring for the regressor is R square. What is the default score for a classifier? It is accuracy. That means the default metric for crosswell score is max is being better. Okay, max is better. R square maximum value is better. Similarly, accuracy maximum value is better. But for the regressor alone, minimum value is better, right? RMSE, we are dealing with RMSE score. Small is better. So to communicate that meaning to the crosswell score functionality, okay, don't think default max is better. Say, for example, the fold 1 returns 5.46, fold 2 return 4.32, fold 3 return 3.78. Normally, what crosswell score function will think max is better. This is not better. This is $5,460 as a bias error. This is not better. This is better, right? So to indirectly communicate to the crosswell score function, this negative prefix is attached. That is why this neg root mean square. Simply, if you print the result, it will show you the value with the negative sign. Okay, this negative sign is for the internal communication, for the internal understanding of the crossword score. This is not for the user. We know it very well. Only the absolute value is needed for us. So I take absolute value of the results. I print the mean and standard deviation. So mean is going to give me the bias error and standard deviation is going to give me the variance error. Okay, now we'll run this crosswell score first for model 2, then we'll do it for model 3. Okay, K-fold I have not imported, right? So the first model we are trying, all the layers that we are using SIG model activation. You follow the same strategy, okay? Only first you define only first layer model.add dense 50 and then do the evaluation and see the performance. If the performance is not satisfactory, increase the number of neurons and then re-evaluate. And then introduce the next layer, then introduce the next layer. Like the way how we have tuned the Scikit-Learn each layer, the same manner. I have come up with a rough configuration like this. So I'm not saying this is the best one. Still, it is fine-tunable. Okay, almost this combination is 95 to 98%. It's the best configuration. Still, there is a scope, 1 or 2% scope. I always leave it to the audience. Okay. So for your combinations, your choices, you can try this. So look at the performance for the model 2 architecture, $3,290. What is the bias error? This is the best score by any other nonlinear model, $3,290 plus or minus $590. Whereas the other nonlinear models like a random forest and all, I have already tried random forest, KNN. KNN does not have that much high variance error, but random forest will have high variance error. Random forest, you will have a variance error around $750 to $900. Even though the bias error will come pretty closer to this, like a $3,800, but random forest will have high variance error. So this architecture gave the score. Let us try model 3, DL underscore model 3. So whether the sigmoidal activation function goes well for this. Here also, all the layer I didn't use ReLU. First two stage I used ReLU. The third stage I used sigmoid. And still, you can experiment all three stages also. ReLU you can experiment. So model 3, here you need to go and change model 3. And then perform crosswell score. Let me write the model 3 score over here. $3,410. $3,410. Please understand, since why we are using this is now it makes sense, because we have frozen 5 folders, the same records I'm validating. Suppose, imagine if I not use this directly, if you use number 5 over here, when you second time when you try to validate the second model, your data also gets shuffled over here. Next, the question will come whether the result, the change in the result is just due to the change in the architecture or change in the samples. Okay. So that is the reason. Imagine a situation, a teacher conducts a test for 2 different sections. Okay. A batch, A section and B section. A different question paper for A batch, a different question paper for B. And the teacher says that, okay, A batch or A section has performed well. The class average is 85% with a standard deviation of, let's say, 30 marks. Okay. Section B average is, okay, average is 70% with a standard deviation of 25 marks. So what naturally the concern will say, they will go and see their question paper. Sir, for section A, you have asked relatively easier questions. So what we do to standardize this process, let me keep the same question paper for both the sections. And then I just try to evaluate the performance. Something like here, I have to freeze the every fold sample same, and then I change the architecture and see which architecture performs better. So many people, they directly write the number 5 here, whatever the fold size, without explicit defining this one. It will lead to some misjudgment. You have to be very careful. Because you set the random state. The moment you set the random state, you freeze. You freeze each folder sample same. Then you try to, you're bringing 2 different architecture and you verify whose performance is better. It's $620. Obviously, the first architecture outperforms the second architecture. In terms of bias error, also slightly high. In terms of variance error, also slightly high. Here you can play around with this. Okay, you can play around with this. So instead of the third layer, also if I use all 3 layers, if I use ReLU, what is the impact? It will be poorer than the score, or it is going to be better than the score. We'll see. So whatever the combinations you wanted to try, you can experiment. Okay, so that's what I'm telling you. Both the models, even though I say this is the best model, still it has 1% or 2% scope for finer refinement. Okay, I just leave that for your experimentation. See, if the best is achieved by me, you don't have any scope for better fine tuning, right? There's no room for you to play with or experiment with. So always I just leave 1% or the 2% finer refinement as a scope to the learners. You can play around and try to see whether marginal improvement in the score is possible or not. Yes. Yeah, okay. Because it's being a regressor model, this output, because they relieve most of the negative valued outputs to 0, okay. So when the computation which uses in the denominator 0, it goes to infinity. So being a regressor model, make sure that last layer you don't use the review, but sigmoid you can use. Being a classifier problem, that issue won't happen. So we fix, okay, out of these two architecture, with the sigmoid activation function, we have got the best possible score. And still you can try to see any further enhancement possible by little bit playing around with the number of neurons and also playing around with the tan h. You just try with the tan h. Tan h, simply you can type tan h. So all those experimentation you do and see whether any better fine tuning. But whatever you have done, you do. Definitely, it's not possible to bring below $3,000. I have already experimented extensively. Maybe marginally you can improvise. So whatever we have got around $3,300, maybe you can bring it to $3,200, around $50. Similarly, in terms of variance error from $610, maybe you can bring closer to $550. So that marginal improvement is possible if you little bit